I apologize. It is 4 minutes after already. I apologize. So, all right. So, welcome everybody. And that's as we start today a sequence of 2 lectures by Henry. Will be, I think there will be a pause of 1 week between the first and the second lecture. But anyway, the first one is today. And here's Henry. Henry, please take it away.
Okay, great. So now is when I stop seeing your faces. All right. So just to make sure, can everyone see this little hand on the screen making circles right now?
I can see.
Okay, great. All right, so let me start. Thanks, Andre, for the introduction. So first of all, before I say anything else, everything I will say in these 2 talks will be essentially material for my thesis, which I think by now is accessible somewhere on Academic Commons. It's of the exact same title as the one written here. So if you want a reference for anything being said here, you should look at that. Okay, so since the topics of the titles involve material from many different places, I want to start with kind of an extended overview of all the objects involved and what the goal at the end of these 2 talks will be. Okay. So the core object in some sense that we start with is a Nakajima quiver variety, which we'll call MQ. And what's a Nakajima quiver variety? This question is answered in n different places. We start with a quiver, okay, and this quiver has 2 types of nodes. One are these round nodes and the other are these square nodes. We'll associate a square node, which is a framing, to each round node, okay? And then we pick the dimensions associated to each node, and we look at representations of these quivers into vector spaces. And in fact, we take T star of the space of all such representations. Okay. And then we do this procedure called the algebraic symplectic reduction with respect to GL of these round nodes. Okay, so the vector spaces associated to these round nodes we usually call V, and the vector spaces which are associated to the framings we call W. Okay. So this is a fairly big class of varieties. And so generally when we work with examples of these varieties, we're thinking of essentially 2 cases. The first one is where you have a single round node with a single framing. And what you'll get as the Nakajima quiver variety out of this quiver is T star of the Grassmannian. And depending on how you pick the dimension vectors, you'll get the Grassmannian of K-planes into n-dimensional space. If in addition your single node has a loop attached to it, then you'll get this moduli space of instantons of rank R on C2. I guess the slightly more well-known example of this is when the rank R is 1, in which case this will be the Hilbert scheme on C2. So these will be our 2 primary examples of Nakajima quiver varieties for today and also the next talk. And acting on these Nakajima quiver varieties is a torus, which will be the maximal torus of some larger group. And let me just name the components of the torus that we're interested in. The first one is a C star, which will scale the symplectic form. Okay, so note that the Nakajima quiver variety starts off with T star of an affine space. So that's clearly symplectic. After you do the symplectic reduction, you still have something symplectic. So these are all symplectic varieties and they carry a symplectic form. And so you're free to scale this symplectic form with a certain weight, which we'll call H bar inverse as a matter of fact. And then you also have this residual freedom to act on the framing vector spaces with GLW. So remember, in our symplectic reduction, we only modded by GL of the round nodes. And so you have this residual freedom to act by GL of the framing. So the maximal torus of that we'll call TW. That's another equivariant degree of freedom that you have. And for certain, I guess for a lot of these Nakajima quiver varieties, you have extra equivariance, which is not included in these two things which I just named. So for example, like I said, if you take rank 1 instantons, if you take the Hilbert scheme of C2, you have this freedom to scale the axes of C2 by a two-dimensional torus whose weights I'll call X and Y. The way I've written it here is slightly misleading maybe, because it could be that the most natural way to add this extra equivariance already includes this H bar factor. So if you choose to scale the C2 by weights X and Y, then it turns out that H bar inverse should be X times Y. It should be embedded as the diagonal torus. But anyways, the point is you have all this equivariance that you can work with, and we will work with this. For convenience, let's note that inside this whole torus T, there's a subtorus which preserves the symplectic form. It's slightly smaller. It's essentially everything but the except the H bar factor, and sometimes it's more desirable to use this smaller torus, which we'll call A, than it is to use T. Okay, so that's the geometric object which we want to think about, and here are some things which are known about it. So this is very much a whole info dump of things. Okay. So the first thing which is very remarkable about Nakajima quiver varieties, and actually this is why Nakajima first introduced them. Well, it's not exactly true. It's one of the main applications of Nakajima quiver varieties is that if we take their equivariant K theory with respect to this T, and I should say very quickly, equivariant K theory, this is the K group of all coherent sheaves, all equivariant coherent sheaves on this space. So you can take this object, and this object turns out to be a representation of what's called a quantum affine algebra, UQG hat. And so what's this quantum affine algebra? It turns out that if you fix a quiver, there's some Lie algebra which can be associated to it. If your quiver is some Dynkin diagram, this is exactly the Lie algebra associated to that Dynkin diagram, but this is a more general construction than that. Your Q doesn't have to be some particular Dynkin diagram. Anyways, so you can take this Lie algebra and you can affinize it, and then you can quantize it. And this is what we mean by a quantum affine algebra. It's some fancy quantum group. Okay. And it turns out to act on the equivariant K theory of Nakajima quiver varieties. And this is very nice because it means that if you care about the representation theory of quantum affine algebras, here's some geometric realization of its representations. And conversely, if you want to study the geometry of Nakajima quiver varieties, it might be helpful to use certain representation theoretic tools. And in fact, the equivariant K theory of a Nakajima quiver variety has a very specific form in terms of a module for this quantum group. It will look like the tensor product of a whole bunch of what's called evaluation representations. So these are very special representations of quantum affine algebras. And roughly speaking, what's an evaluation representation? Well, I guess I should first say, roughly speaking, what's this G hat? If you start with the Lie algebra, adding a hat essentially means now you're thinking about loops into your Lie algebra. So very roughly speaking, it's where you take your Lie algebra and you will join a new formal variable called T or something. Here, I guess maybe we're calling it U. And so what's an evaluation representation? It's a usual representation V of G, And the way you promote it to a representation of G hat is you make this new loop variable act by the scalar U. And so that's an evaluation representation. And geometrically, it turns out what these scalars mean is that they will be exactly the equivariant weights of this framing torus. Okay. So this is a fairly deep and intricate story. And I won't try to recap all the intricacies of it here. I think it suffices for us to remember that these equivariant K-theories become modules for these quantum affine algebras. Okay. So this whole work was due to Nakajima about 20 years ago. Okay. The second thing we know, which again, I'll just state as a huge info dump, is that actually there's a nice way, a nice geometric way to obtain these quantum affine algebras, which will not require you to write down certain generators and relations presentations of these quantum affine algebras. So at this point, maybe I should say, if you look into a lot of the representation theoretic literature, a lot of it starts by writing down certain presentations of these huge quantum groups in terms of certain generators, certain relations. And I have a lot of admiration for people who can look at these giant lists of formulas and really extract meaningful statements from them. But I'm not really one of those people. And so it turns out that there's a nice geometric way to work with these quantum affine algebras, which will not require us to work through all the algebra. And this geometric approach is the formalism of stable envelopes, which was originally due to Okounkov. And later for us, because we're working with K-theory, stable envelopes in K-theory, I think were first written down in this paper by Okounkov and Symmetric. So what are stable envelopes? These are correspondences inside the K-theory of your quiver varieties. And they're correspondences which take you from the fixed points under this smaller torus A to the entire quiver variety. Okay. And they're uniquely characterized by certain conditions, which I don't really want to go into here. Suffice it to say that the characterization of these stable envelopes make it fairly explicit to compute them. Like you really just write down certain big matrices and you do some kind of like row reduction procedure. And so what happens with these stable envelopes is that you can use them to recover this thing called the R matrix. And the R matrix is an object which is associated to quantum groups, specifically for us to our quantum affine algebras. But the converse is also true in the sense that if you give me the R matrix for a quantum affine algebra, I can run this procedure due to Fadeev, Reshetikhin, and Tareyev to reconstruct the entire quantum affine algebra just from its R matrix.
That's Takhtajan.
Oh,
The T is Takhtajan,
yes.
yeah.
Thank you. Thank you for the correction. Yeah, there's a lot of T's out there. T is Takhtajan, yes. Which is why from now on I'll just refer to it as the abbreviated version FRT. Yeah, Reshetikhin and Tareyev is something different. Thank you, Andre. Anyways, so roughly speaking, how this FRT reconstruction goes is as follows. So you compute this quantity in terms of stable envelopes. And this quantity will be an operator, which will act on the K-theory of a certain a certain Nakajima quiver variety. And the way you should think about this is that we'll take a Nakajima quiver variety and we'll pick the framing to split into two parts. One part will be acted on by something trivial, and the other part will be acted on by some weight u. And what will happen to the K-theory is it will also split as the tensor product of two of these evaluation representations. The first one will be associated to the first part of the framing, and the second part will be associated to the second part of the framing. And the second part carries this weight u. And we'll take the R matrix acting on this object. And what the reconstruction procedure does is it says that the algebra that you want to recover is exactly the algebra of matrix elements in the first factor. Okay, so imagine you take matrix elements of R in the first factor, then you get operators acting on the second factor. And these operators are exactly the operators inside your quantum group. Okay, so we'll see a very explicit example of this very soon. But roughly speaking, that's how it goes. Those of you who have seen quantum groups before may be wondering what this parameter q means in terms of geometry. Q turns out to be the square root of h bar, at least in the two examples that we're thinking of. Okay, great. So that's what's known. And so now let me say what's new. So what's new? So what's new is we want to generalize the story in a specific way. So to recap, what's the story that we're trying to generalize? On the geometric side, we have stable envelopes acting on the K-theory of Nakajima quiver varieties. And these K-theories are these evaluation representations for quantum groups. And on the representation theoretic side, we study these representations that we get from the geometric side. In fact, if your quiver is of finite type, then these representations are always finite dimension, and so they actually form they actually span all finite dimensional representations. And so you get a very effective way to study from geometry the representation theory of quantum affine algebras. And so the way we'll generalize this story is as follows. Okay, so we will end up with still having stable envelopes, and they will act on a related but slightly more complicated object, which I think we may get to by the end of today. And essentially what this object will be is, so if we think of a Nakajima quiver variety as some moduli of quiver representations, this new, more complicated space will be a moduli of descending flags of the same kinds of quiver representations. Okay, so it's very intimately related to the original Nakajima quiver variety. The less than or equal sign here is supposed to remind you that the flags are descending, and the arrow up here is supposed to indicate that now we're thinking about flags as opposed to just single quiver representations. And instead of taking the usual equivariant K-theory of this space, we'll be taking what's called the critical K-theory of this moduli. And the reason we want to do this, okay, I don't want to get too much into that right now, but suffice it to say that critical K-theory is in some sense usual K-theory, but it measures it's like an invariant of the singularities of your space. Okay. So it's the growth in the K group of what's called Orlov's singularity category. So it's usual dB co, but you mod by all perfect things inside it. Anyways, So the point is that this will give you some kind of geometric realization of certain asymptotic representations of something. Okay. And so what do I mean by an asymptotic representation? I mean this semi-infinite tensor product of the evaluation representations that we started with. Okay, so if you start with an evaluation representation v of u, I want to think now about these infinite tensor products where the evaluation parameters increase in some kind of geometric sequence. Okay. And specifically, it's a geometric sequence with ratio h bar. And the critical k-theories of these new moduli will sit inside these semi-infinite tensor products as certain irreducible representations. So why is this interesting? It's interesting because on the representation theoretic side, you can use these stable envelopes acting on these spaces to obtain an R matrix as in the previous picture. And you can run FRT reconstruction on that R matrix, and you will get something which is related to the quantum affine algebra that you started with, except what will happen is that certain shifts will necessarily be introduced. Okay, and these shifts will indicate by this superscript mu up here. I will write down a more precise definition later. But the point is that we will get certain special representations of these shifted quantum affine algebras. And the representation theory of shifted quantum affine algebras is slightly more complicated than the representation theory of usual quantum affine algebras. So already you get some mileage out of this. And what's extra interesting about these representations is that even when Q is finite type, these will in general be infinite dimensional representations. And so they're not fitting inside this category of finite dimensional representations, but they will still live in some suitable notion of category O for these shifted quantum affine algebras. And so what you get out of this is some kind of geometric representation theory of certain representations of shifted quantum affine algebras. And I suppose if you're a representation theorist in this area, this is fairly interesting. Now, on the other hand, we can also run this in reverse. We can also say, maybe we can use the geometric representation theory of these shifted quantum affine algebras to study these moduli of flags of quiver representations. And that for us will be one of the main goals of, if not today, certainly by the end of the second talk. And I'll say more about that in 1 second. Here maybe is a good place for me to give some references and credit to some people. Certainly this idea of thinking about these asymptotic infinite tensor products of modules is certainly not new. That idea has been around since ancient times. And the study of modules of this particular form, where you take evaluation representations in some geometric sequence, was first systematically done for quantum affine algebras by Hernandez and Jimbo, where they used a precursor to this language of shifted quantum affine algebras, where essentially instead of thinking about the entire shifted quantum affine algebra, they took some quantum Borel inside it. We'll see later that that's also a very productive viewpoint, though in full generality, it might be better to work with the entire shifted quantum affine algebra. And this geometric input into the study of such modules with this critical K-theory of these moduli of flags, this I first learned from a work in progress of Nakajima and Okounkov. Yeah, hopefully if I keep saying work in progress, it really will become a work in progress and appear soon. Anyways, so right. So here let me introduce one piece of notation, just for notational convenience, which is that we'll call these critical K theories, these flags of quiver representations, we'll call them, well, I don't know how to say this. We'll just write this, right? V with an arrow on top and a less than or equal sign to indicate that we're thinking about descending flags. And this will sit inside all chains of quiver representations, okay, which will notate without the less than or equal sign. And in a completely analogous fashion, it turns out there's no real reason you have to make your flags descending. You can also make them ascending. And the alternate way to phrase that is instead of thinking about the semi-infinite product where you go by powers of h bar to the right in some sense, you can go by powers of h bar inverse to the left and still think about descending flags. So we'll notate that by V with the arrow pointing in the other direction. And so very, very analogously, we can also think about descending flags inside this semi-infinite tensor product pointing in the other direction. Okay, so that's a piece of notation. And so now let me talk about an application of all this to enumerative geometry, which at least for me was the initial motivation for studying these representations of shifted quantum affine algebras. Okay, so what's the enumerative application? So first let me fix a very special representation. Okay, it will be the equivariant K theory of the Hilbert scheme of points on C2. And so what's this equivariant K theory? As a module, so all these equivariant K theories live over the equivariant K theory of the point. So as a module for that ring, it has it's spanned by certain basis vectors, which are indexed by 2D partitions. And I think for now, that's all we need to know. So that's a certain module, okay. And there's a theory of an enumerative theory of curves inside threefolds due to Donaldson and also to Thomas. And here maybe is not the best time for me to give a recap of what DT theory is about, but suffice it to say that in DT theory, a primary focus is to count certain configurations of 2D partitions. And here count is being used in some very general sense. You
mean 3D or?
Well, I kind of mean 2D in the sense that we want to view these 3D partitions as a whole bunch of 2D partitions placed side by side. But yes, you are, of course, Andre is entirely right that when we place these descending flags of 2D partitions side by side, you get what's called a 3D partition, possibly with legs. Legs are what happens when you have an infinite stack of things sticking out in 1 or 2 or 3 directions. But for us, we'll only think about the one-legged case where we And that's just because we're thinking of these 3D partitions as some infinite flag of 2D partitions. Okay. And so per our notation, we'll say that these things live in this module, which is built from f of u, this what's called the Fock representation. It will be infinite descending flags of elements in the Fock representation. And for those of you who have some familiarity with the DT moduli space, this the space of infinite descending flags is expected to be the critical K theory of the one-legged DT moduli space. It's expected in the sense that it's still mildly conjectural at this point. Right. So that's essentially DT theory in a really small nutshell. In a related there's a related theory to DT theory due to Pandharipande and also Thomas. This is called PT theory. In some sense, PT theory is a more efficient version of DT theory, where we recognize that certain contributions are always present inside DT theory, and we don't want to pay too much attention to those contributions. And so we mod out by them and we get this leaner, more efficient version. And PT theory also has a very similar combinatorial flavor to DT theory. You're still counting certain configurations of these cubes. But as you can tell from this picture here, it's not exactly the same as just infinite flags of 2D partitions. But the upside is that, again, in the simple one-legged case, the way you can describe the combinatorics of PT theory is that if you take the complement of the boxes that you're interested in, so if you imagine you have this infinite cylinder that extends all the way into the infinite z direction, if you take the complement of everything that's drawn here, then you will get this descending flag from the negative direction. And in our notation, the way to say that is once you take the complement, you get an element of this f of u business, except the semi-infinite product is in the negative powers of h bar direction. But we're still thinking about infinite descending flags. Okay. And so like I said, certain weighted sums over all these DT or PT configurations, these will form some huge power series, which will involve the equivariant variables like x and y and maybe h bar. And these huge power series will capture something about the enumerative geometry of curves inside three-folds. In fact, they capture almost everything of interest. And so it's highly desirable to gain some kind of control, maybe representation theoretic control over these power series, which count these DT or PT representations. And so what is known is that if you just start off with the Fock representation, so just 2D partitions, then you can run this this story with the R matrix acting on the Hilbert scheme of C2 and so on. And the quantum group that you get out of this is what's called the quantum toroidal algebra, the quantum toroidal GL1 algebra. Okay, so this, morally speaking, is a quantum affine algebra, but you plugged in an affine Lie algebra to start with, except GL1 hat is not really an affine Lie algebra, but morally speaking, that's how you think about it. And so it's known that this quantum toroidal GL1 acts on this FOC representation, this thing whose basis is indexed by 2D partitions. And in fact, it's a lowest weight irreducible representation for this quantum toroidal GL1. And this fact has been known for a while. It's due to multiple people almost simultaneously, I think. But now what's new from our more general construction in terms of critical K-theory is that we get shifted versions of these quantum toroidal GL1 algebras, which act on these new modules, which I'll call dt and pt very suggestively. The module dt mu here is a 2D partition. This module dt mu has a basis, which is indexed by all dt configurations like this, where the infinite leg it has profile, which is the 2D partition mu. So here, in this particular picture, the infinite leg is like 3, 2. And more generally, of course, you can study dt configurations with any fixed infinite leg. The same goes for PT representation. The same goes for PT theory. And you get this PT module, PT mu, which also turns out to be a module for a shifted quantum toroidal GL1. And these modules, to the best of my knowledge, are new, though there are precursors which can be found in the literature. For example, we have a group of people who produced a group of papers studying something very similar to our dt mu modules, but not for this shifted quantum toroidal GL1. Rather, they study it for the quantum Borel inside here. And this PT mu, I think, as far as I can, as far as I know, I don't think anyone's really studied it. It has been suggested that there is some shifted quantum toroidal GL1 acting on some module whose basis is indexed by PT configurations. This was first suggested, to the best of my knowledge, in a paper by Kyoto and Rubchuk very recently. But I don't think they have a systematic construction of this PT module.
Also, those are algebras over a field, whether you have like a...
These are also algebra, yeah.
Whether you have it really over, certain ring, so it's...
Right. That's entirely correct, right. Right. Yeah.
And geometrically, that's very, very different. So to have somehow geometrically have a geometric action which is over a field, it's a relatively weak statement because.
Mm-hmm. Yeah, that's entirely right. Okay, so it turns out that the dt mu module is again a lowest weight irreducible representation. The PT mu one is a highest weight one because we're thinking, for the FOC and DT representations, we're thinking about starting with the minimal configuration, and we're thinking about adding boxes. And we also think about PT in the exact same way, but because we took the complement, if you add boxes to the actual configuration, you're subtracting boxes from from the actual thing which we care about inside PT. So it will be a highest weight representation of this shifted GL1. And what will happen is that we can show some schematic relation which looks like PT mu is the dual of the DT mu module, which is some representation theoretic statement which categorifies certain wall crossing formulas for DT and PT invariants. So if we take this relation in between the DT and PT modules, and you take Q or QQ characters of it. So Q and QQ characters are like the quantized analogs of classical characters for Lie algebras. If you pass to Q or QQ characters of these modules, you'll recover exactly this power series I mentioned earlier, which is called the vertex. And so taking Q or QQ characters of this relation, you'll get certain relations in between DT and PT vertices. And these relations are commonly known as wall-crossing formulas due to a certain geometric relation in between DT and PT theories. So these such wall-crossing formulas for DT and PT theory have been widely studied since DT and PT theories were first introduced, and it's very interesting to obtain some representation theoretic approach to these formulas. Okay, so that was the extended overview of the whole story. So maybe I'll pause very briefly here and ask if there are any questions. Okay. So if there are no questions, then for the remainder of today, what I want to do is instead of writing down the whole abstract theory, I want to really explicitly write down what it looks like in the simplest case of G is equal to SL2. So UQ SL2 is as simple of a quantum affine algebra as you will find. And the corresponding Nakajima quiver variety is also as simple of a geometric space as you could wish for. It's the cotangent space of P1, which I've drawn here. And so I want to work through this example very explicitly. And in some sense, this example is representative of the overall theory. We'll see how to do this FRT reconstruction. We'll see what happens in the asymptotic limit to produce the shifts. Yeah, everything will be very explicit. Hopefully this will be useful to see. Okay, so let's fix some notation. So here we have T star of P1, and the torus acting on it has a weight H bar as usual. H bar is the weight of the symplectic form. H bar inverse is the weight of the symplectic form. And we'll have this weight U, which will act on the actual P1 itself by scaling one coordinate. Okay, and so I've drawn the torus invariant curves inside P1 here. Okay, so the horizontal line is the P1, and these somewhat vertical lines are the cotangent fibers. Okay. And I've indicated their weights here. On the representation theoretic side, we'll write V for the two-dimensional defining representation of SL2, and we'll write its two basis vectors as up and down, following very old tradition spin chains. And so the first order of business is to construct UQ SL2 hat from the R matrix. And I really want to do this in some detail because it's the exact same procedure which is followed to reconstruct shifted versions of UQ SL2 hat from what's called the asymptotic R matrix. So first we'll do the standard case. So how does it work in the standard case? First you compute the R matrix for not just T star P1, but the relevant Nakajima quiver variety is T star of the Grassmannian into C2, which has three components, right? It has the Grassmannian of 0 planes in C2, which is a point, the Grassmannian of 1 planes in C2, which is T star of, which is P1 and the Grassmannian of two planes in C2, which is also a point. And the computation of stable envelopes for T star of P1 is fairly standard and also written down in more than one place at this point. So I won't spend time on that. But the end result is this 2x2 block matrix you see here. If you compute certain compositions of stable envelopes. And so the answer for the R matrix looks like this. And this R matrix will act on the tensor product of two copies of V, essentially. Okay. And here I've hopefully written down what each row corresponds to. So this is the R matrix for V and V. And so what's the reconstruction process for UQSL2 hat? Now that we've written down this matrix, it's actually really straightforward. I will do something that's slightly more complicated than is minimally necessary, which is that we'll first take this R matrix and we'll do an LU decomposition on it. So we'll write it as the product of something lower triangular, something diagonal, and something upper triangular. And the only reason I want to do this is so that the matrix elements we extract later actually match up with a more standard presentation of UQSL2 hat. You don't have to do this. You could start with the R matrix itself and start extracting matrix elements all you want, and you'll end up with exactly the same algebra. But it will be in a slightly different presentation. So we'll factor the R matrix like this, and we'll just start extracting matrix elements, and we'll give each of these matrix elements a name. This 2x2 block matrix here we'll call E. These 2x2 blocks along the main diagonal we'll call psi1 and psi2, and this 2x2 block we'll call F. Okay. And so these 2x2 blocks, these are matrix elements in the first V of this R matrix. And so these will still be operators acting on the second copy of V. Okay. And so what's UQSL2 hat? The reconstruction process says that UQSL2 hat is the algebra generated by the coefficients of these E's, F's, and psi's once you expand them as power series in U. Now there's two catches here, which is one, you can expand around U is equal to 0 or U is equal to infinity, and you'll get two different things. We need to take coefficients of both. Okay. The second thing is that if you just use psi1 and psi2 individually, you get UQGL2 hat. And if you want SL2 hat, you gotta take the coefficients of psi2 over psi1 as you would expect. And so very concretely, if you plug this R matrix into your favorite computational software and you ask it to do the LU decomposition, you'll see that the 2x2 block corresponding to what I called E is this. Okay, if you want to write it as a matrix element, it looks like this. And so if you expand it around U is equal to 0, you get something. If you expand it around U is equal to infinity, you get something else. But each coefficient looks like the 2x2 matrix, which is just 0, 1, 0, 0, up to the scalar, which is root h bar minus root h bar inverse. And so actually the more conventional way to write this is if you call the expansion around infinity E plus and the expansion around 0 E minus, the more conventional way to write it is you do E plus minus E minus. And so you get this infinite series in both negative and positive powers of u. This is E of u. And we can see from our very explicit 2x2 matrix that E of u looks like this. Here small delta is the standard delta function, and E up down is standard basis. So it's zeros everywhere except for one at the place indicated by up down. Similarly, you do the same computation for F, you get something very similar, and psi looks like this. And you should already kind of recognize that this is the evaluation representation, because if you ignore this whole business with u, these operators for E and F are exactly the standard representation for SL2. And pictorially speaking, we can envision the coefficients of these E's, F's, and psi's drawn on some kind of lattice like this. So here I've drawn all the coefficients of E arranged by their exponents in U. Here's F. And for various reasons, we don't combine the positive and negative parts of psi. We treat them individually. So psi plus is these black dots, psi minus is these red dots. Okay. Let me introduce some notation at this point, because we'll need to work with weights of our representations sooner or later. Just like usual Lie algebras have a theory of weights, quantum affine algebras have an analogous theory of what's called loop weights. So now instead of like eigenvalues of a single operator in your Cartan, you think about an infinite series of eigenvalues for each coefficient of psi plus and psi minus. And these series of eigenvalues form rational functions, and these rational functions are called loop weights. Okay, so here, this is the loop weight of the eigenvector up of psi, and this is the loop weight of the eigenvector down of psi. Okay. And once you have a theory of weights, you have a theory of highest loop weight representations and lowest loop weight representations. And so in the case of our two-dimensional V of u, you can either view it as the highest weight irreducible corresponding to up arrow, or you can view it as the lowest weight irreducible corresponding to the other vector. And we'll write them as L of a weight and L check of a weight to indicate the highest weight irreducible representations and the lowest weight irreducible representations. There is some convenient notation you can introduce for these rational functions, which will appear as loop weights, which is this whole business with the what's called the symmetrized symmetric algebra, S hat. And the notation is essentially that S hat of a single monomial in your equivariant variables is this function. Here, this subscript u is just there for convenience. U remember is our evaluation parameter, and having this u here just means every time x appears, u appears with it. And this S hat is defined to be a homomorphism for these weights. So S hat of the sum of two weights is the product of their S hats. So as an example, this loop weight of up arrow can be written more succinctly as S hat of 1 minus h bar inverse. If you're not familiar with this what this asshat business, you should check that. It makes computations slightly more succinct later. Okay. So that's that for UQSO2 hat. So now we have a complete description of how it acts on the two-dimensional evaluation representation. And it will be very helpful to keep this, especially this schematic picture in mind for later when we talk about the shifted versions of UQSO2 hat. Okay, so that's step one. Step one was to first say what UQSO2 hat is. Step two of our computation is to try to understand what these tensor products look like in the finite case. So I said we in the end, we want to study these infinite tensor products where the evaluation parameters increase by powers of each bar. But the first step is to understand the finite case and then to send the length of the tensor product L off to infinity. So how do you understand this? Here it turns out that, again, reconstruction is very helpful because not only will it reconstruct the quantum affine algebra as an algebra, it also reconstructs it as a Hopf algebra, in fact, as an entire quantum group. And so it will explicitly say for you what the coproduct of elements in your algebra is. And once you know what the coproduct is, then you know how they act on tensor products. And so then you know what this whole tensor product will look like. And so how do you recover the coproduct? It's actually very tautological in some sense, right? We recovered elements of the algebra by taking matrix elements of R. If you want the coproduct of a matrix element, you take the exact same matrix element of the R matrix for the tensor product that you're interested in. So if you're interested in V1 tensor V2, the R matrix for that thing by axioms of an R matrix will be the product of the R matrix for V1 and the R matrix for V2 with respect to this auxiliary space V. So very concretely, if you think back to our 4x4 matrix up here, if you want the coproduct of E, all that you have to do is you take the product of two of these matrices, now acting on a threefold tensor product, V1 tensor V, V tensor V, and then you take the exact same matrix element inside its LU decomposition. Okay, so that's how it goes. And so again, I won't write down the explicit details here because that's not super helpful. But what you can do is you can just run this computation. It's fairly straightforward and not too long. In the case of V of U tensor V of U H bar. Okay. And you'll get these formulas for the coproduct. Okay, they're fairly okay. Usually, so here's maybe a suitable place to say that there's actually no known formula for the coproduct in terms of these Drinfeld, in terms of the presentation which I've stated for the quantum group. So it's nice that here we have some fairly straightforward formulas, but you shouldn't expect it to be this nice in general. Anyways, such tensor products are
Speaking
very
of
well
in
studied.
general, it's I think you shouldn't expect any kind of presentation in general. Like, you know, this is
Well,
that's my favorite. It's kind of my favorite point. I swear I have to make it. You know, if you have an algebra, it's, you know, you shouldn't expect it to be given by generator's relation. The same way if you have an algebraic variety, you shouldn't expect to know exactly its equations.
okay, maybe I should be slightly more specific about what I mean by in general. I essentially mean outside of this case. outside of maybe like T star of the Grassmannian, possibly the Hilbert scheme, where the formulas are in some sense still manageable. Okay, anyways. Right. So tensor products of evaluation representations of this particular form have actually been very well studied since Chari and Presley 30 years ago now. And it's known that this particular tensor product is reducible. And we can actually see the reducibility by our formulas. You can actually do the computation because you know exactly what this looks like. It's spanned by pairs of ups and down arrows. And you can see that there's actually no way to get to this particular basis vector from these other three. So for example, if you start with up, up, and you try to lower it in the hopes of lowering the first up arrow into a down arrow, you'll see that this coefficient of f turns out to be 0. There's some kind of conspiracy that happens for specifically this choice of evaluation parameters. Okay, and the specific conspiracy that happens is you end up with some delta function with an extra factor which specifically multiplies with that delta function into 0. Okay, and this conspiracy is not an accident. We'll see why this happens later. Anyways, so we see that this twofold tensor product will decompose into some 3-dimensional thing and a 1-dimensional thing. And if you try to do this more generally with an else,
I think a direct sum sign is slightly misleading here.
Sure. Yes, that's yeah. Here maybe this is actually a non-trivial extension. Thanks, Andre. So maybe I'll write. I don't know. That's right. Just a regular plus here. Right. Okay. Right. So maybe I should say that this 3-dimensional thing is the submodule, and this 1-dimensional thing is the quotient. If you try to do this more generally with an L-fold tensor product, what you'll see is that there will always be one submodule which is given by descending flags of these arrows. And because we only have an up arrow and a down arrow, a descending flag just means, you start off with some number of up arrows, and then the rest is all pointing down. So we'll focus on these submodules of these L-fold tensor products, the notation for which I've written here. Okay. And in fact, you can compute that this submodule of descending flags of arrows is a lowest weight module, lowest loop weight module. And as you might expect, the lowest weight vector is the one where all the arrows are pointing down, right? And you should imagine that the action here is by raising operators. Every time you act by E, you just try to raise the leftmost vector, which is pointing down. And you can compute specifically what the loop weight is. Okay? And that computation is fairly straightforward because the coproduct of these psi's is of a very particular form. It's sum on diagonal terms. So psi tensor, psi, and so on. And everything else is off diagonal, and it's off diagonal in a very specific way. In such a way that if you apply psi to a lowest weight vector, it turns out to just be the product of the psi's of each individual vector. So you get the product of each individual eigenvalue. And this product telescopes into a much simpler thing. And again, it's this cancellation here is not an accident. There's really something very special when you specialize these evaluation parameters into this particular kind of geometric sequence. Okay. So that's what happens for the L-fold finite tensor product of these evaluation modules. And there's essentially nothing super special happening here. Okay, these are still modules for UQSL2 hat. As I've said, you can really explicitly describe what this particular submodule looks like. What's interesting now is to send the length of this tensor product off to infinity. And in this asymptotic limit, there's two interesting phenomena which occur. The first one, which I think is the most interesting, is you notice that many R matrix elements, they will develop singularities in the sense that so recall that to recover the algebra, the quantum affine algebra, we took coefficients of matrix elements of the R matrix, right? At U is equal to 0 or U is equal to infinity. And what will happen as L goes to infinity is that singularities will appear in these matrix elements. And you can already see one such singularity in this loop weight, which we've computed. Okay, so if you ask yourself, what's the loop weight of the lowest weight vector as L goes off to infinity? So now we have an infinite chain of all pointing down arrows. This loop weight has this prefactor of H bar. You can, what's the way to put it? You have a freedom to pick if your equivariant variables are less than 1 or greater than 1. Here we'll pick the convention that H bar is less than 1. And so if you send L off to infinity, you kind of have a problem here. This whole thing has a pole of a certain order in H bar. And in fact, poles of this form are the only poles which will appear in the R matrix. Because when you think about it, when you extract matrix elements of the R matrix, like you say, I'll extract like the VWth matrix elements. There's only like a finite number of raising and lowering operations you can do to get from V to W. And everything else that happens in every other tensor factor must be a product of these psi's. Okay, so the only singularities which will appear, the only infinite products which will appear are actually infinite products of these loop weights, of these eigenvalues of psi. But that remark aside, I mean, you do observe singularities appearing in the R matrix. And these singularities are what will cause the shift, which I mentioned earlier, and we will see this in 1 second. So that's the first observation. The second observation is a kind of combinatorial observation, which is that in the finite L case, okay, so in the L-fold tensor product, if you take the vector of all up arrows, of course you can still lower this, right? You can apply F, and what the lowering operator will do is it will lower the very last up arrow. And that will still give you something which is a chain of descending arrows. The thing which happens when you pass to L equals infinity is that now you have this infinite chain of up arrows, and you don't have a very last one. So there's actually no way to lower this vector anymore. Any way of lowering this vector will result in something which is not an infinite descending flag of arrows. And so the corresponding coefficient of your lowering operator will be 0. So actually, in the case of SL2, in the L goes to infinity case, we'll get 2 different lowest loop weight submodules. And these will both be modules of descending flags. The first one will be generated by this vector of all up arrows. And if you think about it, that's actually the trivial representation, because you can't lower it, but you also can't raise it, right? So it's actually isomorphic to the trivial representation. And then you have the submodule, which is generated by the vector of all down arrows. And this one is actually more interesting because, of course, now there's non-trivial things you can do to this vector of all down arrows. You can raise the first one, and then you can raise the second one, and then you can raise the third one, and so on. And so you get some infinite dimensional submodule of descending flags of arrows. And so the notation we'll introduce for these submodules is we'll write V with an arrow, less than or equal sign to indicate we're thinking about descending flags. And over here, we'll just write the vector, which is like the asymptotic of your flags, the thing which your flag eventually converges to. Okay, so V down arrow is the module of all descending flags which are eventually down arrows. And V up arrow is the module of descending flags, which is eventually all up arrows. Okay, so that's our notation. And that's the second observation. Okay, so now let's turn back to the singularities in the R matrix. What we want to do is still end up with some well-defined R matrix, which hopefully satisfies the Yang-Baxter equation and all the properties you want in an R matrix. That way we can use the R matrix, we can push it through FRP reconstruction, and you'll get some quantum group acting on these asymptotic modules. And so the way we'll do that is we'll take the naive version of the R matrix, which is acting on this L-fold tensor product as L goes to infinity. And we'll just manually remove the singularity. And the alternate way of stating this is we'll take the leading order term as L goes to infinity of the R matrix that you want. So if we look back at the R matrix, in the case of this particular vector, we see that the singularity looks like H bar to the minus L over 2. And actually that is the leading order singularity. That is the leading order term for this module V down arrow. And so if you want the R matrix for this asymptotic module V down arrow, we'll just cancel out that singularity and we'll take the leading order term. And the leading order term is still some R matrix. You can show that if you repeat this with all of these asymptotic modules, the set of all such R matrices, they really will be R matrices. They really will still satisfy Yang-Baxter and so on. And I guess in some sense, that statement is not really something you have to show. It's really tautological. So as an example, right? What's the lowest weight? What's the loop weight of this infinite vector of all down arrows? It will be exactly this expression we wrote down earlier here without the singularity. So it'll be this product. this product again, oh, I guess I've simplified it already. So you send L to infinity, it becomes this rational function. Okay. And in a completely analogous fashion, you can get the appropriate R matrix for the other module, the up arrow. Okay. And so these like leading order R matrices we'll call asymptotic R matrices. So that's how you construct the asymptotic R matrix associated to one of these asymptotic modules. It's important to note at this point that the singularity, the order of the singularity in H bar will change depending on your module, depending on your asymptotic module. Okay, it will change depending on which vector you've picked here, whether you pick up arrow or the other choice. But, yeah. And so now that we have an R matrix, we can ask, what does the quantum group reconstructed from it look like? And the answer is it's very similar to UQSO2, but it's not exactly the same. And the primary reason it's not exactly the same comes from these psi's. So let's look at this eigenvalue, this series of eigenvalues, right? If you expand this rational function around u is equal to 0 and u is equal to infinity, around infinity, the expansion lives inside here. It has no constant term, and it starts from the first order term. And this shift of that series is something that's not present in UQSO2 hat. Okay, so in UQSO2 hat, or in any unshifted quantum affine algebra, these psi plus minuses always start from the constant term, and the constant term is invertible. In fact, the constant term is just the classical weight. But here we have a shift where the constant term is 0, and you're starting from the linear term, which turns out to be invertible. And if you look at what happens for the other asymptotic module corresponding to things which are eventually up arrows, the up, you'll see that the weight of the loop weight of the lowest weight vector is 1 minus u over h bar. And again, if you quote unquote expand this rational function around u is equal to 0 and u is equal to infinity, you'll see that again, there's a shift. But now it's a shift in the opposite direction, where you used to start at the constant term. Now you have a pole. Now you start at the -1th term. Okay. And so what this means for the actual series psi plus and psi minus is that, of course, they also have to start at shifted places. Okay. So in the case of like in some sense, a positive shift here, psi is missing a coefficient in comparison to the unshifted case. And in the case of here, psi has this extra term at -1 in comparison to the unshifted case. And so in general, this leads to the general notion of a shifted quantum affine algebra. So what's a shifted quantum affine algebra? First, so here I'll say for SL, I'll say the actual definition with SL2 in mind. But as I've written it, there's nothing special here to SL2. Except, of course, you'll have more E's and F's and psi's than just one set of them in the more general case. Anyways, so the shifted version of SL2 hat will depend on two parameters, mu1 and mu2. These will be two shifts. For SL2, these will be two integers, but more generally, they should be co-weights. Okay. And what do? They specify for you how much you shift psi plus and how much you shift psi minus. So if mu1 is positive, that means you have extra coefficients in psi. Psi will start at some negative part. And it's fairly straightforward, I think, and also fairly believable at this point, to see that actually you don't have to specify independently what the shifts of psi plus and psi minus individually are, because you can just shift the entire picture up and down by multiplying psi, e, and f, all by some power of u, such that, so you could pick your favorite convention for this, but it seems like in the literature, people like to shift it so that psi plus has no shift and psi minus has a shift by mu. And mu here is the same as mu1 plus mu2. So from now on, that's the picture we'll keep in mind. Psi plus, these black dots start at the constant term. And psi minus might start later or before. Okay, so for example, if mu is positive, then psi minus starts earlier than it should. So there's extra coefficients, which will mean you have, in some sense, extra elements inside your shifted UQSL2 hat. Okay, so that's what shifted quantum affine algebras are in a nutshell. So the only modification is this shift in the psi's. Everything else stays the same. All the relations stay the same as well. And that's not too hard to convince yourself of from the asymptotic R matrix picture. So these, I think here maybe I should say, these shifted quantum affine algebras are the idea of having a shift is by no means new. The shifting goes back all the way to 15 years ago, for where it was first introduced in certain specific cases. Here for the cohomological analog of all the stuff I've said. So for Yangians, and also in type A. And then later works successively generalized this to, I guess, arbitrary mu, to the K-theoretic setting of quantum affine algebras. So very concretely for us in our extended example, we've just constructed two different asymptotic modules for two different shifted quantum SL2s, quantum affine SL2s. The first one is this V up arrow. And I think I wrote somewhere earlier that that's the lowest weight. So it's the lowest loop weight module for the one shifted UQSL2 hat. And V down arrow is the -1 shifted UQSL2 hat. It's a lowest weight module for that thing. And it turns out that V down arrow has already somewhat been studied in the literature. It's called the negative pre-fundamental module, but it's only been studied as a module for the quantum Borel inside this big shifted quantum affine algebra. So much later, we'll see what the appropriate notion of the quantum Borel is, and we'll see what it looks like for these shifted algebras. So this was studied in Hernandez and Jingo. They also have a notion of the positive pre-fundamental module, which for us will be obtained from V up by some kind of induction process, and we'll see that later. Right now for us, V up arrow is kind of not interesting. It really just is the trivial module for the one shifted quantum affine SL2. Okay, yeah, so I think maybe that's a good place to stop for today. next time I will, so what we saw today was a very concrete and explicit computation in terms of purely the representation theory of SM2 path. Next time we'll revisit this picture from the geometric side, and I'll say something about the geometric construction of this moduli of flags I mentioned at the beginning. And I'll also say more carefully things about its critical K-theory. Hopefully after that, we'll be ready to work on our main application to DT and PT modules. Okay, thank you for your attention today.
Awesome. Thank you, Henry. Questions?
This is a really small point, but you said that we could freely choose whether H bar was like less than or greater than 1.
Yeah.
But if we had made the other choice, we would have gotten a minus sign when we took the limit, right? And
yeah, sure. Right. So you let's see. You will get some signs flipped, and you will get some shifts flipped around. Yeah, it's really a matter of your convention.
okay.
More questions? I had two random questions. One is like, for myself, I could never figure out what the shifted Yangian is until this sort of definition with the poles and the R metrics. But that's not the one the Brundan-Kleshov use, right? Is that do they motivate the definition somehow? Is that or is there some other way to think about it that is?
So I don't really have an answer to that because I will admit that I didn't read this Brundan-Kleshov paper in detail. My exposure to shifted Yangians is actually from the second paper on the list and its successors, where they introduced the shifted Yangian by essentially it's completely analogous to the thing I said for shifted quantum.
Okay.
You just take the analog of psi and shift it around.
Cool. And another question: is there any way to I know this is not what you want to do, but suppose H bar was not less than 1, not bigger than 1, but a root of unity. Is there a way to take, like a limit along a subsequence where that thing is?
Yeah, that's an interesting question. I haven't thought about this. Yeah, that would be interesting, right? Because what's going to happen? You'll get this sequence, which itself is not conversion, but like if you have an nth root of unity, you'll have like
exactly. You just along the
sequences.
Exactly. You have a bunch of different sequences.
Yeah, I don't know. Maybe such a phenomenon is kind of reminiscent of like orbifolding. And I don't know. Maybe it corresponds to something about I don't know, maybe instead of Hilbert's scheme of C2, it's the Hilbert scheme of like an ADE singularity. I'm not sure. I haven't thought about this.
Okay. All right. Any more questions for today? Then we thank Henry for today very, very much, and we'll see each other in 2 weeks, not in 1 week, in 2 weeks. Thanks, Henry. We'll see you in 2 weeks.
Thank you all for your attention.